Today we will be discussing about minimum cost spanning tree. First, let us discuss what is a spanning tree. Assume that you are given a graph G, then the spanning tree of the graph G is any subgraph of G which connects all the vertices in G. In other words, the spanning tree of G contains all the vertices of G, but it's not necessary that all the edges in G are included in the spanning tree. Let me explain with the help of an example. You can see the figure that is shown here. It has 7 vertices and 14 edges. If you observe this graph, you can see that some of the edges are darkened and the others are not. And you can also observe that the darkened edges are sufficient to connect all the vertices of the graph. All the vertices of the graph and the darkened edges of the graph together form the spanning tree of the graph. So now you know that the spanning tree of a graph is the set of all vertices and the edges required to connect these vertices together. Please note that there can be any number of spanning trees for a single graph. The only condition is that sufficient number of edges that are required to connect all the vertices together must be included. Now let's see what is a minimum spanning tree with this simple example. Here you can see a simple graph and there are a set of numbers which are written on the edges of the graph. These numbers are the weights of the edges, or it is also called the cost of the edge. Now here you have a spanning tree of the given graph. The weight of this particular spanning tree is equal to the sum of the weights of all the edges that are included. So in this case it is 7 plus 5 plus 3 plus 4, that is equal to 19, which is the weight of the spanning tree. Here you have another spanning tree of the same graph where a different set of edges are included. You can see that the weight of the spanning tree is also different. 7 plus 5 plus 2, that is equal to 14. Now again you have another spanning tree of the same graph, and here again a different set of edges are included, and the weight of the spanning tree is 3 plus 4 plus 2, that is equal to 9. You may also please observe that this is the spanning tree which has the minimum cost or the minimum weight. So out of all the spanning trees which we have seen, this spanning tree has the least cost or the least weight, and hence this is called the minimum cost spanning tree. Now that you know what is a minimum cost spanning tree, there are two algorithms which can be used to find out the minimum cost spanning tree of a graph. They are Prim's algorithm and Kruskals algorithm. Out of this, we will be discussing the Kruskals algorithm. The Kruskals algorithm applies the greedy strategy to find out the minimum cost spanning tree. Now, before you go into the details of Kruskals algorithm, it's important that you know what is a forest in data structures. Now, please feel free to skip the video in case you already know what is a forest. In simple terms, a forest is just a collection of trees that are disconnected. The image shown displays a graph that is disconnected. It consists of 3 trees. Now, this is an example of a forest because it consists of a set of trees and the trees are disconnected. So now let's see how the Kruskals algorithm works. The Kruskals algorithm works by treating the graph as a forest. Now, in order to construct a forest from the graph, just remove all the edges from the graph. So now what is left is a set of vertices which are disconnected to each other. So each of these vertices form a tree, and the collection of these vertices form the forest. Now the Kruskals algorithm starts working by adding edges one by one to this forest. As we have already discussed, the Kruskals algorithm follows the greedy strategy, and in the greedy strategy, at each step, the best option available is selected in the hope that ultimately the optimal solution can be achieved. So here, when the edges are added to the forest, the edge which has the minimum cost is selected first. Then the next minimum is selected next, and so on. Let's consider the previous example. So in order to construct the forest from this graph, first of all the edges are removed. Now the edge which has the least cost is added to the forest first. Then the next edge which has the least cost is added. and then the next. So this forms the minimum cost spanning tree of the graph. Let me explain the algorithm in a much more formal way. The first step would be to remove all the loops and the parallel edges. A loop is an edge from a vertex to itself. If it exists, just remove the loops. If there are two edges between the same set of vertices, they are parallel edges. In this case, keep the edge which has the minimum cost and remove the other. Now arrange all the edges in the increasing order of the weight. Now add the edges to the graph in this order. That is, the least cost edge gets added first. And continue this procedure until all the vertices get connected. If a circuit or a cycle is formed while adding an edge, just discard the edge. Let me explain in detail using a more complicated graph. Here you can see that there is a loop at vertex C and there are also a set of parallel edges between edges A and B. So here, as per the algorithm, we remove the loop, and in the case of parallel edges, the edge which has the minimum cost is kept and the other is removed. Now the remaining edges of the graph are sorted in the increasing order as shown in the table below. Also the edges are grayed, which indicate that they are removed and not present in the spanning tree. It's not necessary to draw the grayed edges. So as we can see, BD and BT are the two edges which have the minimum cost, and hence these two edges are first added. The black color of the edge indicates that they are added to the minimum cost spanning tree. The next set of edges which have minimum cost, AC and CD, are also added to the spanning tree. The next edge to be added is BC. But you can see that if BC is added, there is a cycle formed between the edges B, C and D. Hence, we skip the edge BC. The next edge which we can add is BT. But you can see that when you add BT, again there is a cycle formed between B, T and D. So you discard the edge BT as well. Now the next edge which you can add is AB. But you can again see that if AB is added, there is a cycle formed between A, B, C and D. So you skip AB as well. Now all the discarded edges are removed from the graph in this figure. The next edge which is added is SA, after which SC may be added, but you can see that if SC is added, again there is a cycle and hence SC is also discarded. So this is the final minimum cost spanning tree of the given graph.